Okay, so today is going to be a lot of work. But you've got the notes, and so you don't have to write everything down. But I think that we get into the first law and then immediately start applying it. So with thermodynamic calculations, and since next week is the beginning of the calorimetry labs, then it's time to start talking about the calculations that you'll be doing in lab. So a lot of the stuff that we talk about today, glad that everybody's here, so that you can be real well prepared for the next 3 weeks of lab. So that's going to be good. All right. Oh, I got to plug this through that in. Here we go. Yes, and so this is the law of conservation of energy, or the first law of thermodynamics. We'll see it in a couple of different forms in this course, but it's talking about the internal energy of an isolated system being constant, and we'll tear apart each one of those pieces. Now, you already know what the internal energy is. We calculated that. It's, even from a quantum standpoint, it's the probability of each energy level times the energy level's energy. And then we will talk about these other terms in this part of the course. We'll distinguish between work and heat. And heat is Q, not the partition function. Okay, we'll talk about enthalpy. We'll get into thermochemistry, but you've already done thermochemistry, but we'll review it again. We did it in the lab as well, where you take products minus reactants. So delta H, delta G, delta A, and so on. We did that in the last course, in the last section of the course too. Hess's law, where you can take, if you have known delta H's, you can use the reactions kind of like algebraic equations, where you can add things to the left and to the right. As long as you do the same thing to both sides of the equal sign, you're legit. Okay, same in chemistry. Think about the reactants arrow. I mean the chemical reaction arrow. If you put water on the reactant side and water on the product side, you're fine. You're adding something to both sides. And then we'll touch on group contributions a little bit. Actually, the group contributions thing is very similar to the QSPR that y'all are doing. We'll discuss heat capacity, state functions, and then we'll apply thermodynamics. So this word in the first law, where it says isolated system, that's a very important word. So let's talk about that. So we have 3 types of setups. We have an open system where the mass and the energy can leave. So this is the important piece right here. Can matter and energy leave? If so, that's called open. And so we're focusing on the matter and the energy. If we don't let the matter leave, then it's a closed system. And if we could put energy in or pull energy out, then we can put energy into the whole system and it can be held on. So what do we always say? We always say don't heat a closed system, right? Because you're going to build pressure, and then the container may break. So it may become open, and that's not good. And then over here is an isolated system. So if we have insulating walls and we have a sealed or closed system, matter can't leave and energy can't leave. And that's what we want for our like our ice chests and thermoses and stuff like that. So the number one, well, I don't know if it's the number one. It kind of depends on the situation. But a major problem with isolated systems that we want to have like a cooler is actually cold air leaving and hot air coming in. So the mixing of air. And so that's why those Yetis have such a strong lid, because that's the number one place where you lose all of your heat and interact with the environment, is a leaky lid or opening and closing that lid. Same with ovens. You're trying to get the oven checking on the food, you're fanning that oven, you're letting all the hot air out, and then it has to get back up to temperature. And so you can really ruin a recipe by constantly fanning the oven. So, practical knowledge here today. Okay. Now, if we have a cooling steam, like 1 mole of steam cooling from 373 to 298, notice that we use this negative sign here to show that heat left the system. So a lot of times you have to figure out, what are we talking about in terms of the system? So if we call this cooling steam, steam is the system. And if it's cooling, the heat is leaving. And so it has a negative sign. So we're talking about the system. And so this is the convention that we use in this course, that all of our heat flows and so on are from the perspective of the system. A lot of times when we have a chemical reaction, the reactants and products and the double arrow and so on, that thing is the system. And so whenever we have an exothermic reaction, we're saying that reaction lost heat to the surroundings. Therefore, delta H is negative. So the negative sign means it was lost. Okay. And so when we compute the change in, or the temperature rise of the surroundings, notice that if this is the system and it lost heat, it went into the surroundings. So the surroundings always change that sign of the system. Okay, so the system, the heat lost by the system, that's a negative sign there. We want to know the surroundings. We change that negative sign and we know that it was positive. The surroundings gained heat, the system lost heat. Equal and opposite signs. And so this is what we see, this equation all of the time. And I guess you'll see me emphasize this a bunch of times today, that there's always a place where people lose, they drop a negative because they think that this negative sign right here in this definition of the surroundings equals minus the system is this negative sign right there. And it's not. Okay. There's two negative signs. And so a lot of times they see that negative 1870 and they think, okay, the negative sign's already in there. Same kind of thing we did with the equilibrium constant expression. I even saw it on a couple of exams where it was e to the minus delta g over RT, and they dropped the negative. Now here's a couple of other ways to state the first law of thermodynamics. The internal energy of an isolated system is constant, or energy is neither created nor destroyed. That's probably the more common one that people see. But then because of E equals mc squared, okay, they've changed it out to mass energy is conserved. And so you could convert mass to energy, but it's that combination of mass or energy is conserved. You could say energy is conserved if you take into account if you lost mass, it's turned into energy. So you're still looking at mass energy. So that would take into account, say, nuclear transformations. So what do we mean by energy? Well, this is a really, I think it's a decent way to think about energy. What is a joule? We define temperature as that property that things share when they're at thermal equilibrium. Okay. Doesn't really tell you what temperature is, though. Like this, we're talking about ontological language. Like, what is something? Okay, what is energy? We really can't nail it down, but we can say if I have energy, I can do work with it, and if I don't have energy, I lose the ability to do work. And so we really talk about energy in a utilitarian way. We don't really know what it is, but we know what it can do, and we know how to find it. We know how to create, turn some things into useful energy. And so energy is a system's capacity to do work. And so the system gains energy when work is done on it. For example, winding a spring, compressing a gas, etc. And the system loses energy when it does work. So when that spring unwinds, then it's done work. When gas pushes a piston, it has done work, and the system has lost energy in the form of work. The system can also gain or lose energy in the form of heat. And so I like to think of energy as the currency and work and heat as the method of exchange. Like I can use cash or credit. We can say cash is work and credit is heat. Okay. But do you see how energy is the thing that's being exchanged? And there's two ways to exchange it, work and heat. That's a really important concept. So if that confuses you, let's clear it up now. So all this time with the thermodynamics, the statistical thermodynamics, we were calculating these terms like enthalpy and Gibbs energy and all of that. But now we're going to really focus in on what we can do with those different terms. So how we can use that energy to make machines go and to warm our food. So work is the fundamental property in thermodynamics. And the reason it's the fundamental property is because it's measurable. So it's equivalent to moving an object against an opposing force. I'm sure you always go back to your days in physics when you're like trying to figure out how can I make this system lift a mass against gravity, and then I could calculate the amount of work it did. It was working against a force for a given distance, and so I know that the amount of work that it did. So if you have a rotating system, that rotating system could be hooked to a pulley and pull a mass up against gravity. You could calculate the change in height, gravity, and so you know the mass, and so you can tell how much work was done. We do the same thing with gases. We put them in a piston, we put a mass on top, we push that mass, and so we know how much work was done. These are all sort of mental constructs as to how we can calculate how much work was done. It's like raising a weight, expanding a gas against an external pressure, driving an electrical current through a resistance. We have equations for all of these, and so we could calculate the work being done. So when I say work is measurable, for a measurement, we really need to see non-random motion. So that's really the difference between the work and heat, is we look at the surroundings and let the surroundings decide. So if we have the surroundings, so the system is losing energy, it's going into the surroundings. Is it cash or credit, right? Is it work or heat? Well, if it's creating random motion in the surroundings, then we would call it heat. If it's creating ordered motion in the surroundings, we would call it work. Because again, we can use ordered motion. If it's pushing a piston, right, we're getting an ordered motion in one direction. We can connect that to a stick that goes around a crank, and we can turn something. Then we can turn our wheels and drive our cars. So all we're doing in a combustion engine is using hot gas to create ordered motion. We're pushing a piston in a certain direction. We're taking that linear motion and turning it into rotational motion using a crank. So in your engine, you have a piston, you have a tie rod that ties it to the crank. And so once we get it going in the correct direction, then it'll just keep turning that crank. And so that's how it works. We'll see more detail on the construction of engines in the middle part of the course. So there's like 5 portions. The middle part is the exciting one where we get into engines. So here's the first law in action. The total energy change is made up of the system and the surroundings. And the shortest version of the first law is that the total energy of the universe is unchanged. Right? Energy is neither created nor destroyed. And so the total equals energy. Therefore, the system and the surroundings are equal to each other, but with opposite sign. So one of those is negative. Either the system is negative and the surroundings is positive. Therefore, we have that opposite sign in the middle. They're equal and opposites of each other. And so this is without electrical or chemical or phase changes, then there's only heat and expansion work. So we'll stick with those for a while. We'll just heat things up. And they'll cool down and they'll create disordered motion in the surroundings, or we'll expand and push one of the walls of the container, like maybe a piston, or maybe we'll expand into the room against a constant pressure, like heating a beaker. The gas that evaporates, we can think of it conceptually as if there's an invisible membrane over the top of the beaker, and when it expands, it's pushing back 1 atmosphere of pressure. So even though you can't see the ordered work, it's doing work. It's pushing back against the atmosphere. So it's hitting those molecules and pushing them out of the way as it leaves the beaker. So we could calculate that, even though we don't actually see it. We can certainly use it by putting a real cap over the beaker and causing it to push that cap or piston. And so this is the key equation for this part of the course, is that this system loses energy or does work. It either loses energy as heat or does work if it's if the energy system is negative. If it's positive, we're putting energy into the system by either heating it up or doing work on it. So you can compress a gas with a piston, and you're doing work on that gas. So you're putting energy into the system. Now it's at a higher pressure, has a higher energy. And so we saw that internal energy was the energy of all of those little energy levels and how they're populated. Now, a lot of those were translational energy levels. In fact, that was the largest component for most of the gases. And so that was the kinetic energy. Those were the energy levels of translation. Internal energy is a state function. So let me talk a little bit about a state function. It does not depend upon how the system was prepared. So what do I mean by that? Well, think about if you're on the second floor of this building. You could calculate your energy relative to the ground floor by just calculating your weight and how high you were. And so you're on the second floor. You now know how much energy you have. Does it matter if you got there by coming up from the first floor or coming down from the third floor? It doesn't matter. That's the energy you have at that height above the ground. You could also go up the stairs. You could go up the elevator. And so stairs and elevator would be a kind of the difference between work and heat. You know, there are just two ways to get energy. I could do work on the system and get it to a certain energy, or I could put heat into the system and I could get it to a certain energy. And so because it's a state function, it doesn't depend upon the path. So it doesn't depend upon stairs or elevator or coming down or going up. All I need to know are the state variables of the system. So what are the state variables? State variables are, we'll talk about gases, the ideal gas law. So what are all the variables in an ideal gas law? PV equals nRT. So there's 5 things, and one of them is a constant, R. All the others are your state variables. So if I know the pressure, the temperature, the volume, and the amount of material, then I know the energy of that system. And if I change the volume or change the pressure or change the temperature, I can calculate the change in energy of that system. Okay? And it doesn't matter if the volume expanded to get to that point or was compressed to get to that point. I can calculate the energy of that system if I know the state variables. And so we'll have a discussion later on about what's called an equation of state. And the ideal gas law is your first equation of state. So it's an equation that tells you what state you're in, what kind of energy you have. And the nice thing about it, for these equations of state, all you need to do is calculate final minus initial to get the change. So if I went down the elevator to the first floor, I could calculate my energy change. If I went down the stairs, I calculate the energy change and I get the same answer. Okay? But if I was concerned about how much work I did, those paths are important. And so for work and for heat, they're path dependent. So let's say the stairs are heat and the elevator is work. So if I went to the second floor using the stairs, that would be like heating a gas up to a certain pressure. If I was to use the elevator and get to the second floor, that would be like taking a gas and using a piston to compress it to that volume that corresponds to the second floor. And so that would be doing work on the system. I'm compressing it, so I'm doing work on the system to get it to a certain energy. Or if I take something in that volume and I heat it up to get it to that pressure, then that's adding energy by heat. So heat and work can change the energy. So we have this equation here. Again, we have final and initial, but we don't have that sort of the heat final and work final. We have changes in variables like change in temperature final or volume final, pressure final. So we can calculate the change in energy. So let's use an example here. So we have this piston. We have an external pressure up here, so P external. It's pressing on this whole area, and we're moving a distance Z. And so you see our three distances. Area, say, would be centimeters squared, and then the distance in centimeters, so that's a volume. So we sweep out a volume, so we're changing the volume of the system, and that's what we're doing when we do a piston. So when a piston of area A moves through a distance, it sweeps out this volume of A dz. And that external pressure is equivalent to a weight pressing on that piston. The force is the external force times the area of that piston. And so this is why we designate the displacement volume of piston engines. So again, it's related to that amount of force that we can have. You have a larger area of the cylinder being pushed, that piston being pushed, you have more torque because that area is directly related to the force that you have. And so you can have like a high performance little bitty engine that runs at high RPMs, but each of those pistons is really tiny. You get it on a hill, it can't go because it doesn't have a lot of torque. Okay, so we had a friend of mine who drove a Geo Metro back in graduate school, and there was a bookstore in Oregon where I was going to graduate school up in Portland. And it was Powell's Bookstores, famous bookstores, like a whole building in Portland, and several floors. But the parking garage ramps were so steep that his little car wouldn't make it up. And so it had 3 cylinders. It was 1 liter displacement. So like my truck is 5.7 liters. So this little Geo Metro, 3-cylinder engine, 1 liter displacement. So each one of those cylinders, 3 cylinders, was 1/3 of a liter in terms of how much it displaced. And he had a big dog, and we were all in that car, and we got up that thing. It was like, we could not get up the hill. And he said, you and the dog are going to have to get out. So we got out, and he was barely able to creep up. He was burning out his clutch just trying to get up the hill because he would let out the clutch and the engine would start to die. So he'd push the clutch in and roll back, and it was pretty funny. So again, that was directly related to his tiny little pistons in that engine. He got great gas mileage, though, as you might imagine. Okay, so if we plot that displacement of that piston on a PV diagram, so we have pressure here and volume here. This is what's called an indicator diagram. And so that system pushes a piston back against a constant external force. The area under the curve of the indicator diagram is equal to the absolute value of the work performed by the system. So this area here is proportional to the work done by the system. So if you sweep out a longer stroke, then you have more work. If you work against a higher external pressure, then you have more work. And that's why diesel engines are more efficient than gasoline engines, because they operate at a higher pressure. And so that's one of the advantages of a diesel engine. So this is the equation here. The work is calculated by that external pressure times the change in volume. And change in volume is always final minus initial. That's a huge area where students make mistakes. Okay. Pay attention. We're predisposed to wanting positive numbers when we take a difference. If I give you 2 numbers and say subtract them, you're probably going to take the larger one and subtract the smaller one. And this is final minus initial. So if the final one is smaller, you're actually subtracting the larger one. That's where you lose a negative sign. So if you're predisposed, you just have 2 numbers, and I know I got to take the delta V. Do not mess up and take the larger minus the smaller. You got to pay attention to what is the final minus the initial. So I always try to point out where I see students year after year make mistakes. That's one of the best places that you'll get caught on. We're just predisposed. We're going to subtract 2 numbers. We take a bigger one and subtract the smaller one. That's not what you're doing here. Okay. So expansion and compression are also important. When that final volume is larger than the initial volume, that's expansion. when the final volume is smaller than the initial, that's compression. So you're squeezing it into a smaller volume, that's compression. And so we see that same thing up here in that diagram with the volumes. Now we could get a little bit more work out of it if we weren't working against an external, like a constant external pressure. So if we were able to go slowly, a little more slowly than just popping the top on something and expanding into against constant pressure, if we were to actually look at the ideal gas law as it changes with terms of volume, so P equals nRT over V, you see that over here? If I can find my pen. Here's my pen. Okay, it's in there. All right, so P equals nRT over V, so that's that isotherm. We have a constant temperature, constant set of material, amount of gas, but we're changing volume and we're mapping out the pressure. See that? And so that's that inverse relationship. And so this is what's called an isotherm. Okay, so constant temperature. And notice how we can get a little bit more work out of it. And so this is what's called reversible isothermal expansion. So the system is held at a constant temperature that requires it to be in contact with something that as it expands, it wants to cool. And so this thing is continually putting in heat as it expands. Or when you compress it, it wants to heat up. And to keep it isothermal, you need to sink the heat out. And so this reversible isothermal expansion, you have to have heat flow into or out of the system so that you can maintain that constant temperature. And so this is good for slow-ish expansion only. And so let's look at this. How do we calculate the work done? So we can take the, if we go slowly, we do just a little bit of work by just a little change in volume. And so let's do that work. We'll calculate the volume final and volume initial, and we'll integrate that dV. And so we can change pressure here to nRT over V. And so now we have V in the denominator. So we're integrating with respect to V. And so that we can pull the constants out front. And then this is a known integral that's the natural log of V final minus V initial minus the natural log of V initial. And so whenever you have that subtraction from the integral, that ends up giving you the ratio of V final over V initial. And so this is a really important equation, and you will use it frequently if you see things like reversible isothermal. So if you're talking about reversible isothermal expansion, this is the equation you use. This is really why it's critical for you to practice the problems, but also have that note card so that you can look at the situation and say, oh, is it against a constant pressure? And it's the previous equation. If it's reversible isothermal work, then use this equation. So let's do some super simple practice here. So calculate the expansion work done with 55.8 grams of iron reacts with hydrochloric acid to produce hydrogen gas. And here's the equation. That's our system in two scenarios. One, in a closed vessel of fixed volume. Okay. So that's always a trick question. You're asked how much work is calculating. You're sitting there trying to figure out which equation do I use. But in both equations, you're looking at delta V, right? And delta V in a fixed volume container is 0. And so no work is done in the first scenario. You take the chemistry content exam on the graduate record examination, the GRE, that's probably one of the questions. Once again, you're looking at the vocabulary, and it's more of a concept question. You're saying if there's no change in volume, there's no expansion work done. What about the next one? An open beaker at 300 Oops. So let's go ahead and calculate that. If we have 55.8 grams of iron conveniently, that's 1 mole of iron. Okay. And so typically what I'd like to do is look to see 1 mole of iron. Is this balanced? Yeah, we got 1 mole there. We got 2 chlorides, and then the 2 hydrogens make hydrogen gas. And so that's a 1-to-1 ratio. So 55, I'll go ahead and do the whole thing. Then we have the mole ratio. All right, 1 mole of H2 gas. Now, what's the volume? So that's going to expand out against, let's see, an open beaker. So we're at 1 atmosphere pressure, open beaker. So that's going to expand out to the final volume. So we have 1 mole of hydrogen. We'll assume that it's room temperature, all over 1 atmosphere. You may say, well, I know what 1 mole is. It's 22.4, but that's at standard temperature and pressure, not at 298. So in this one, we end up with something else.
So for me, my own wouldn't stay at 300. That would be our.
Oh, does it say 300? Oh, 300 Kelvin. I'm sorry. I just assumed room temperature. So 300 actually. Thank you. Thank you. 25.5 liters. Yeah. Okay, so that's the V final. What is V initial? So remember, this is reactants to products. So initially we have all reactants, and this reaction proceeds in the forward direction. We'll say it goes to completion as a good first guess. How much hydrogen do I have at the beginning if I only have reactants? 0. None. Right. So 0 liters. Okay. And so this is expansion against a constant pressure. So it's minus P external delta V. So minus 1 atmosphere times 25.5 liters, that's V final, minus 0 liters. So it's 25.5 liter atmospheres. That's the work. Well, that's not a very clean number, is it? Work is equal to 25 point, and minus, sorry, minus, because it's expansion work. I don't want work in liters atmospheres. So how do I get out of that? What would I want work in if I'm doing work? Joules. Yeah, I want an energy unit. So how do I get out of liters atmospheres and into joules? I could dig around in the definition of an atmosphere, turn it to pascals. I'm going to take liters and get it out of that and maybe into cubic meters or something ugly like that. Do all my unit conversions and everything like that. But you can also use two constants that you have committed to memory. What are the two constants? What are the two gas law constants that you have in your head? R. Now, what are the two units of R? One is I just used here, 0.08206 liters atmospheres per mole Kelvin. What's the other one? We used it in the previous portion of the class all the time. So when we were doing RK, or RT, not RK. So Boltzmann's constant times Avogadro's number gives you R in different units than liters atmospheres. What are those units? Are you thinking or waiting? Joules per mole Kelvin. Joules per mole Kelvin. Okay. So let's think about this. I want to get out of liters atmospheres and into joules. So what if I just did this? 8.314 joules per mole Kelvin. And you're going to look at this and you're like, is that legal? 0.08206 liters atmospheres per mole Kelvin. So the kelvins cancel, the moles cancel, the liters atmospheres cancel over here, and I've got joules. Totally legit. If you can get the units to cancel, that's your roadmap. And so you just multiply that 25.5 times 8.3, divide by 0.082. It should be about 100. So it should be around 2550 joules. Because if you're looking at it, it's 8 over 0.08. Okay. Yeah. And so, so maybe I need to know this. Yeah. Okay. Now, if you do this division, do you know what number you get? That is equal to 101.325. Does that look familiar at all? That number 101.325? It may not, but that is the conversion of atmospheres to pascals. Okay, so there's 101,325 pascals in an atmosphere. Okay, where did the order of magnitude of 3 come from? That was the liters to meters cubed conversion. So we essentially did that long conversion, but just used the two R's. Okay, so you could do it either way; it would come out to the correct equation. But this is a nice shortcut. You've already got both of those constants sort of in your memory on your periodic table that I give out in the exams. So both of those are on there, so you can always use those to go back and forth between joules and liters atmospheres. Okay, next week we're going to start calorimetry. We're not going to be able to get through all of this stuff today. I don't exactly know how I crammed so much into one lecture, but we'll talk about some more of it tomorrow or on Monday. But this is the bomb calorimetry that we're going to be doing. We're going to have a little sample in here. Got a little electric wire that you guys wire up. It's really kind of cool. You make a little fuse wire and sticking it on there. And then we fill this up, stuff it full of like 25 atmospheres of O2. So we really pack in the O2. And then you ignite it. There's a little ignition button and you punch it. And I wish there was a sound or something. It's so anticlimactic. You punch the button and the light comes on and that's it. Then you look at the thermometer and you see the heat the temperature go up, and you're like, hey, it worked, or oh, it hasn't moved, something's wrong. Yeah, and so then, I wish there was a GoPro or something inside there that you could see the sparks and everything flying around. But yeah, it's a vigorous reaction in here. The oxygen tears apart your sample and also chews up some of the wire. And so then you weigh the wire before you wire this thing, and then you weigh the bits of wire left over, and you subtract the difference so you know how much heat came from the wire burning up, and then how much heat came from your sample. And so that's what we're ramping up to. So next week we're just going to put hot and cold water together to get used to the instrument and doing the calculations. Then the following week we'll do some benzoic acid tablets, and then the third week you can bring a sample in within reason. We had people do gummy bears, Fritos, the little pork rinds and everything, but it got pretty nasty. So our pellet press, when you squeeze on a Frito, all the oil comes out, and you're like, oh, or the pork rinds, those were pretty bad. But it was pretty cool with the pork rinds because that's almost all protein. And so this bomb calorimetry, this will be the last comment, the bomb calorimetry really is a good way to get those nutritional values. And so if you bring in your different types of food, you could do, Crisco, which is all fat. You could do sugar, which is all carbohydrate, and you could do protein sample, which is all protein, and see the calories per gram of each of those. And even though you have catalysts and everything, remember catalysts don't change the delta H. Catalysts just change the kinetics. And so the delta H of combustion is exactly the same in your body as it is in the bomb calorimeter. And so this is where you get your nutritional values. You can burn them in oxygen, and your body's just trying to harvest every little bit of work it can get out of that reaction. And so we're doing this with no work because it's a bomb. It's a fixed vessel. It's strange they call it a bomb because it doesn't blow up. It's maybe a potential bomb. So you don't want to put too much sample in there. But the point is, the volume doesn't change. Therefore, everything is heat. And the heat goes into the water, and we measure the temperature change. And so then we measure the enthalpy of combustion. And that would be the same enthalpy of combustion that happens nutritionally in your body. Cool stuff.